Thanks for the introduction. Thanks for the invitation. Thanks for having this be a part of the workshop. My name is Adina. I'm based in Germany. I work in the Institute of Neuroscience and Medicine at the Research Center Jülich in Germany, close to Cologne. And I'm doing a PhD at the University of Düsseldorf. Part of the reason that I'm here today is that I was a Repronym fellow. That's not being like part of the core team of Repronym, but it is being selected as a teaching fellow, where I had a year of train the trainer trainings and support and an excuse for becoming kind of a Repronym, reproducible neuroimaging trainer, and I got to go to institutions and my colleagues and tell them, hey, I'm a Repronym fellow. Why don't you learn about reproducible neuroimaging? I can give you workshops, I can give you some training. And if that interests you, and also if you want to connect more with the crowd of people that are part of, you have already met here, then I simply encourage you to also apply for this fellowship. It's a year long. I think the calls for this year have closed already, but I'm sure Dave will open up the next round next year. So the next winter over Christmas, just write a short application and good luck. And it's a really cool program. I can very much recommend it.
Stay tuned in January. December, January for the next one.
Yeah, great. Awesome. Yeah, I hope that gave you enough time to get a hold on the slides. You could scan this QR code, also find a link in the workshop materials. So my plan for today's session is a mix of live coding, hands-on demonstrations, explanations. So you will see me presenting slides, but you will also see me executing code. And you are very welcome to code along and basically do the same things that I'm doing. If you want to do this, then you can click on this link here on the slides, or you can go to handbook.datalit.org. And when you hit the landing page, go all the way down to code list from chapters, and then it's the very last link. And then what you can find here is everything that I will be talking about today with copy and paste code snippets. So you can click here to have them copied to your clipboard and then paste them into your own terminal. You'll find a little bit of additional explanation, some more links to the things that I'm saying. So this is something that will stay there. If you're interested in just like listening, it's completely fine. You can try it out later. So this thing is for you to work through at your own pace if I happen to be a little bit too fast, maybe. I'm trying to give you a whole overview of things, and that will not only include version control for data, but in the end, I will wrap up a lot of things that you've heard also yesterday, also about virtualization, for example. I'll foreshadow a little bit about reproducible workflows because they are a part of what I'm going to show you. And I'll wrap up by showing you how to actually publish data. So next time you are in the position of, oh, I have this paper that's coming out and I want to make my data available for others, but they are 100 gigabytes and I really don't have like a web server to put them to or something, or I have a web server, but who's going to find it? Then I'll show you a way how to do this for your next study, hopefully also including how to get a DOI for your data in that specific method. For everything else, I'm available. You can hit me up on Twitter, by email. You can take a look at this resource here, the Datalit Handbook, where me and many other people have collected all of the knowledge about research data management and data version control that we have acquired so far. So in each of these chapters here, you can find tutorials and code-alongs and walkthroughs. Alrighty. So there are a couple of things that you will need if you want to do what I'm doing. The first one is to get installation of Datalat that depends on your operating system. And then if you want to code along for the containerized analysis, then you will need another Python package that's called Datalit Containers. You can install this one, for example, via pip or other package managers. And then you will need a container solution. And that can be either Singularity, of which I'm a fan because I often work on compute clusters, or Docker, which probably works on your local machine. Nicely. Alrighty, so let's start and motivate a little bit of version control for data. So you've seen this picture here yesterday, also just now in Per's recap. And this is just the beauty of having your own makeshift version control system with like file extensions that denote versions in really minuscule changes. So in my day-to-day work, I specialize in research data management. And this thing happens so often, but it also happens on quite a large scale. So let me show you one real-world example of a real compute cluster. This is the exact same thing as before. Like in this case, it's directories, but those directories have slightly different names, you know, like version identifiers. It's just that all of these directories are several terabytes large because they contain the very same data set in different stages, in different phases of conversion from different times. Nobody really knows. The file names try to be helpful, but when you see this kind of thing and then you try to use this data, the ENKI data set for your next data analysis, what you're going to do is probably, okay, I'm going to re-download this whole thing to know what I'm actually using. And that's something that on the outside of things looks a little bit like, you know, Git could help here, right? Because you have this kind of self-made extension thing, versioning system where you kind of identify where or what kind of data you have here. So I mean, Dorota already told you that it's not a good idea yesterday, but let's dive into why this is not a good idea. So the thing is that Git is a tool that is made to handle small files, well, text-based files. It comes from a software development standpoint where you have frequently changing code bases, lots of collaborative demands, but the thing that changes is text-based files, and those files are super small. And what Git does in a very, very simplified fashion is you have your versioned code base, or you have your versioned repository. You have all of the files in the repository, and in order to make a version history, Git creates a snapshot whenever you commit. Git is very clever in doing these snapshots. So when you make a commit, but one of the files or two of the files, like in this version 2, don't change, Git does not store a snapshot of those files a second time. So you don't have like an increase in file size from having a snapshot of those files, but it just creates a pointer that says, okay, this file in the second version is identical to the file in the first version. But if a file changes, like file file A1 or file C1, those changed. B is a pointer to file B that says, I haven't changed. Then what Git does is it takes a snapshot, but it stores it in a very efficient way that's not representing all of the file if it's a text-based file, but just a representation of the difference in vastly simplified terms. So over the course of the time that you track your changes in a Git repository, your repository grows with each commit slightly, just really, really slightly. This slightly is because if you version control text-based files, they really just don't increase that much in size, but also because for text-based files and a few other types of files, Git has very efficient storage strategies that help Git to really keep the repository very, very lean. The problem comes when you commit large files into Git. So if you have your maybe you're working with fMRI like I do, if you have your nifty image and it's a couple of gigabytes, when you put that into your revision history, then two things happen. The first is the snapshot that is initially created when this file is added is really large because it's the complete 5 gigabytes. But then whenever you change this file, Git will likely, because for example, a Nifty file is a really special binary file type. Git will not have a strategy to efficiently or even realize what has changed between the two versions of your files. The Nifty image has lots of metadata in its header, and if you just add a tiny metadata field that's like a couple of bytes in size, Git will not be able to see this difference. Git will have to store the complete file again in its snapshot in order to perform the version control duties, simply because it doesn't have an efficient strategy to deal with this kind of file type. So when you version control large files, then you basically bloat your repository. And that can get you, in theory, for quite a long way, but it definitely has performance impacts. So one of the things that you might have experienced is when you clone a repository from GitHub, that it takes a little while to get those repositories from GitHub. The cloning process takes a little while. What is taking so long is an actual download, and what is downloaded is the repository. And that includes all of these past snapshots, because if you have a repository clone, then you are able to take a look at the history, check out past versions, everything that the rotor has shown you. But for this, all of this repository needs to be retrieved. And if you have large files in your repository, then that retrieval naturally takes longer. So you will need to be really patient if you have a lot of files. And then there are also a couple of other operations that will start to become sluggish after a while. Like Git is a powerful, really, really powerful tool. But you'll notice at some point you shouldn't version control a neuroimaging study with Git. It's not fun. Nevertheless, Git doesn't have like a limitation on that. So it will not prevent you from adding large files to Git. The problem exists, though, with the services that you may use together with Git. So if you've ever accidentally committed a large file into Git and then tried to push that to GitHub in order to, have your colleagues play with it, then you might have seen something like this, which is Git refusing to host the changes that you are trying to push because the changes exceed for a single file, a file size limit. And that's a little bit of a mess, because if you are not used to interacting that much with your history, then it can be really quite frustrating to get a file that you put into the revision history out of the revision history. Getting it out is a quite complex and really destructive operation. So that's not cool. So there's not only a little bit of a performance impact that can become quite substantial, and if you overdo it, then you ruin your repository with large files. But essentially, version controlling large files with Git also prevents you from getting the advantages that repository hosting services provide you with. So one solution to this is the tool that I'm talking about today, which is called Datalit. And that is an open source tool, of course. It's available for all major operating systems, and it's a command line tool. So we can revisit the discussion about command lines and GUIs from yesterday if you want to. But if you want to use Datalit, then you actually have to get out a terminal. And for everyone who's here on Windows, I hope that you have the Windows subsystem for Linux installed, simply because the terminal experience is much nicer there than on a native Windows system. Because if you have a shitty terminal, then I'm really sorry that you have this, I can totally see how command line tools are very unattractive if the terminal isn't nice. Datalit is a tool that builds up on Git, but it also builds up on a second tool, and that tool is called Git Nx. And in short, its major features are that it allows version controlling arbitrarily large content. It has transport mechanisms for sharing and obtaining data. It has, beyond version control, means to do computationally reproducible data analysis, and attach provenance of what has happened to your file to your digital objects. And in all of the things that it does, it is completely domain agnostic. So I use it as a neuroscientist, but you can also be a librarian or in any kind of field. I want to give you a couple of examples for what Datalit is used for, of what I use Datalit for, just to give you an idea how the tool is used in practice. For one, it can be used to publish or consume datasets via services that you're very familiar with probably, such as Github or GitLab, or the Open Science Framework. So what you can see here is a screen capture of a GitHub project, and this project is the Human Connectome Project open access dataset that I maintain alongside too many other people. And what you can see is that I can clone it with a datalit clone command. And then what you can see here, and I'll shed light on this later, I can run a command that gives me access to the data from the Human Connectome Project open access. And that's cool because at the time that I recorded this, that data amounted to about 80 terabytes of data, and we updated it recently, so I think now it's over 200 terabytes of data. But what that allows me to do is I get access to 200 terabytes of data by cloning a GitHub repository, and that's quite neat. What it is also used for is as a backend, as a software backend for a couple of services that you might be familiar with. For example, this is the old interface of OpenNeuro. It looks a little bit neater now, but every single dataset on OpenNeuro, where you can share your fMRI, EEG, neuroimaging, whatever data, is underneath the hood a Datalit dataset that you can obtain with the clone command, and then retrieve the data on demand. And it also allows you to go to, in this case, for example, BrainLife, that interfaces with all of Datalit datasets, and then you can analyze those data from those datasets in the cloud. What we also use it for as scientists is to share our work in a way that makes it very accessible and reproducible for others. So here's a paper that I wrote and published a while ago. And what you can see here is that this is also a public GitHub repository, very accessible, nicely findable. And this repository contains software data and code for a paper that we wrote. And if I were to clone this, then I could not only get a transparent overview of everything that has been done in this paper, until it was published. But I can also, in this case, for example, automatically recompute the results. And something that I find an even cooler example comes from a colleague from Berlin who has published a really neat study. But then not only did he publish this as a paper, but he is also a Repronim fellow and is urgently aware of the need to make data available, analysis available, etc. So he created a complete Jupyter book, including all code that runs on data that is version controlled with Datalit and hosted alongside it, so that he has a pipeline where he can just rerun all of his results whenever his data changes. That's quite neat. And then in the institute where I'm working, we use it as a central data management system because we have a lot of data sets that plenty of people use. And we just maintain this data sets collection with all of the data sets that are available to some or all members of our institute. And when anyone needs to have these kinds of data sets, then they can go to our internal GitLab instance and then just get the exact data sets that they need. All right, so before we get started, I'm going to split my screen so that I have a terminal here on the right-hand side and then my slides here on the left-hand side. I hope you can still see everything. And now let me quickly set everything up. So the first thing that I'm actually going to do, and you don't need to do this, is I'm going to SSH onto a shared compute cluster because that gives me a stabler internet connection and a little bit faster downloads. So you can see here that everything I'm doing here is happening in a terminal. And the first thing that I'm doing now is to check if I have a recent version of Datalit installed. And this is also the basic command line usage here. Whenever you type something in the terminal, you start with Datalit and then a command or a command option. And if it returns something like this, like 15.5, that's a recent version, that's great. Now, one thing that you noticed here is that I received like a recommendation and that's a part of the configuration that needs to be done. You will have done this already if you coded along to yesterday's Git tutorial, because what Datalit needs, because it builds up on Git, is also a Git identity and Git email. So if you see this kind of warning, then you can just add your username and user email just in the same way that you have done yesterday with the rota.
Tina?
Yeah.
There's a question that how in the chat, how could one update the version if needed?
That depends on how you installed it, but your package manager typically has like an upgrade function. So this thing is a system-wide installation that comes from apt. But if you've installed it, for example, via pip, then you can say pip install -U Datalit. I think what is the equivalent for conda? Also a capital U pair? Yeah.
Related question, how do I know that 15.5 is current? Yeah, as if Datalit isn't off to 20.7 or something? I don't know.
Or you can check on our source repository. I mean, if you do an upgrade, then it will give you the most recent released version on your package manager. You can check PyPI if you want, pypi.org Datalit. Yeah. Alrighty. So one other thing that I want to mention beforehand, I'm using it in the terminal to do commands, but what you can also do is use it in a programming language of your choice. So Datalit is written in Python, and it has a Python API where you can use its functions by importing it if you code in Python and then calling Datalit's commands within your scripts, within your interactive sessions, and so forth. But if you're fluent in a different programming language, then you can use it obviously also by system calls. So if you use R, then you can do a call like this that would execute Datalit just as well for you. Now, the first thing that we're going to look at are Datalit datasets. And Datalit datasets are Datalit's core data structure. Datasets are simply just a directory that's managed by Datalit, and any directory on your computer can be managed by Datalit. And you can either create them in order to do like local version control or version control something new, or you can install them from different sources if someone shares their dataset with you. And what datasets can also be done is nested or linked, and I'm going to show you the advantages of this a little bit later. The crucial thing is that a Datalit dataset is a Git repository. It builds up on a Git repository underneath. So the fundamental thing that you have is a Git repository, and if you have a Datalit dataset, there's no need to use Datalit commands. If you don't want to, you can also use Git commands. It's completely valid. There's nothing, like, it's just a Git repository. But what it is also is, on top of being just a Git repository, it is also a so-called Git Nx repository, and that adds the version control features for data. Now, first of all, I'm going to show you how you create a dataset, and this is done with the Datalit create command. I'm using a configuration here that I will be explaining a little bit later, but the fundamental command to create a new dataset from scratch is Datalit create, and then followed by a directory name, and this is going to be the directory that will be created and then managed by Datalit. So what happens now is that on the system I have a new directory called bitsdata, and this is a Datalit dataset that is ready to version control my data. Now, a brief detour on how that kind of version control works, given everything that I've told you about the snapshot things that Git does. Git and Git Nx and Datalit are two tools that are developed in conjunction to each other. Git Nx is basically the workhorse that we sit on. It's an impressively powerful tool, and I highly encourage you to check it out if you're interested. It's a wonderfully written piece of software. And Git Nx is the thing that helps with the version control for data with a little trick that prevents your Git repositories from bloating when you add large data to it. What Git Nx does is it keeps your Git repository as is, but it adds a little extra, which is called the Nx, and then it keeps two types of repository, or then your Git repository gets two separate locations for which data can be kept. You can either keep it in Git, which is very useful, as Dorota told you, for example, text files or code. But then anything that is larger, or also stuff that you want to keep private because you don't want to expose it to the Git history, that goes into a secret place that is managed by Git Nx, and that secret place is called the Nx. And then, even though this is the same, and what you then do is you can put your Git repository part on all of the hosting services that you like. Everything will be fine. GitHub will not complain. And you put all of the stuff that you put in the Nx to locations of your choice. And those can be all kinds of third-party services. Lots of free ones are there. You can link it to your Google Drive, your Dropbox account, the Open Science Framework, an S3 bucket, and so forth. And what Git Nx then does is it associates the stuff that's in the Nx and the stuff that's in your revision history with each other, so that you have a teeny tiny pointer, like I'm going to show you that in detail in a bit, a metadata entry basically about the files that are available in the Nx, and then you can issue a retrieve call, and Git Nx will know on which platforms you have stored your data and for whom they are available, and then it will retrieve them automatically. And that makes the distributed version control not only possible for code, but also possible for large data files. So what Datalit does is it sits on top of these two tools and tries to simplify how version control is done a little bit. And it boils down, data management-wise, to only a differentiation between two things: datasets and files. Those are the only quantities or units that Datalit knows. Once you have a Datalit dataset, you can do any kind of modification and then simply save them. And the save will issue that modification to go into either Git or Git Nx, so to say, to the appropriate version control tool. That behavior can be configured, which send where, and shed some light on that. But when you use a purely Datalit-based workflow, then you do any kind of change, add any kind of data, do a Datalit save, and then you're version controlling whatever the modification is. Obviously, you can also use pure Git or pure Git Nx commands to do the very same thing, so it's not exclusionary. If you are a Git Nx fan, then you can just also use pure Git Nx commands if you want to. Alrighty, so let me show you how that looks like in action. So what I'm going to do is I'm going to put a README into this dataset, because this dataset will be a dataset in which I will version control bit structured data. So naturally, I'm creating a README so that I have a human readable entry point. And when I issue this command here, I'm doing it from the command line so that I can remote control it. I'm basically writing what's in quotation marks here into a new file called README. And Datalit status, which is similar to Git status, it just also will do it for large files. It reports then that this directory, this dataset that it manages, has a new untracked file, README. And what I can then do in order to version control this file is to issue a Datalit save command. And in order to make the change human readable in my Git revision history, I can attach this -m, short for --message, to add a human readable description to this change. What I can then do is another change. So I'm going to extend the README file a bit. So I'm echoing, or I'm appending this new line of description to this very same file that is already version controlled. And if I now issue a Datalit status, this file will not be modified. will not be untracked, but it will show up as modified because from its previously version state that we saved, there has been a modification with appending this additional line of text. So what I can then do, if I'm confident, if I'm happy with this modification, I can save it as well. So that is basically the strategy for version controlling stuff with Datalit, and that makes version control a little bit easier than the Git workflow that you've seen. But of course, this is very simplified. You can also do everything that you want with branches. Everything that you can do in a Git repository is possible in this data set as well. But you're basically skipping the staging area here. So if you've paid attention to this neat little graphic yesterday, where you would have needed a git add and then a git commit to stage and then commit the file, here you skip the staging and go straight to committing. Yes?
Or we have a question in the chat saying that when you run the datalet create -c text to bits data, that it's Maurizio getting an error saying that -c and bits data are unknown arguments. Do you have any idea?
Not from the top of my head. It's also like quite hard to see without the exact error message.
If you see, I don't know if you can get your chat again or the Zoom chat. The error message is basically unknown arguments -c and bits data. So these appear to be unknown arguments, at least Maurizio's case installation.
Funky. Maybe spaces. Hard to see. So
could be a version thing. I'm not sure.
I don't know. Yeah, it's quite hard for me to debug this now. We can take a look later. Also because I can't see Maurizio's terminal. Just having this copy and paste snippet, I can't even see if there might be a space between the dash and the C. So I'm really sorry that you're having this trouble, Maurizio. I need to get back later, and you'll be confined to just watching. I'm really sorry. But yeah, checking the version is a good idea. Personally, I haven't encountered it, but really, really difficult to debug as also a presenter.
Yeah, it's weird. I installed it right before the workshop, and still I think that I have an older version than you because it doesn't say 15.5. So,
but
yeah,
what does it say? What does it say?
So the command would be datalet version, right?
Yeah, -- version.
And it says 0.9.3, but
oh god,
but
yeah, but that's
right before the workshop.
Yeah, but that's the problem. I think you're on a WSL thing, right?
Yes, exactly.
So you're probably on Ubuntu.
Yes.
So what I would encourage. So the thing is, we don't have. When you package stuff up for Debian systems, all of the different flavors have their own repository or package hosting, and we do it for Debian, so we have quite good control and can update the Debian stuff pretty neatly. Ubuntu is lagging behind in updating that, but what you can do is you can enable the NeuroDebian repository, which will provide your Ubuntu system with additional sources to install packages from. And this should be, you can find it in the handbook. And then here is a link to NeuroDebian. Here you can also see the availability table. And so you're probably on Ubuntu 18.4 Bionic Beaver, and that's indeed the most recent version available there, which is kind of ridiculous. I think it's 7 years old or something. But if you enable the NeuroDebian repository, you just need to select your operating system. In your case, it would be the Ubuntu version you have installed, and then you can select a download server that's close to your place, and then you have 3 lines. You get 3 lines to copy and paste into your terminal, and then you run if you use apt sudo apt update, and then you should be able to get the most recent version of Datalit installed. It's just that this particular version of Ubuntu just doesn't have a up-to-date package next for this particular package.
Okay, and so you would recommend in general, if we use it in the future, to have a look at these lists on the homepage and look for the latest version, or?
So where I would always look, because it's Python software, pypi.org, Datalit, and then you will always find the latest release right here. And you can also go to GitHub, and that should be here. So Datalit, and then you will see releases here on the right-hand side, and there you will get the most recent release from.
Okay. Yeah, thank you.
Alrighty, sorry for the troubles. Okay, so wait a second, there's another thing in the chat, the commit sudo apt-get upgrade, but there's with base. Okay, there's plenty of installation stuff that I really sadly don't have the time to go into now. So I'm really sorry for everyone who is doing the installation now and has problems. We can meet later. I'll know the answers to all of these problems, but fixing them would take up the complete 2 hours. And I'll show you how you can use it once you have it working. I'm just afraid that you will need to just watch instead of coding along. Thanks for sharing the installation instructions again. All right. So when you do version control, the 2 things that I would advise for Datalit is it's identical to how you use it with Git. You should save meaningful units of change because you want to, in theory, revert them in meaningful units, and to attach meaningful commit messages. And then you can get this kind of nice Git log revision history where you have a complete overview of everything that has been done over the course of things. But what this means is that you can also, now that you have this directory that can also version control data, you can just add loads of data into it and then just save it to version control your data. And then do all of the things that you would be able to do with Git's revision history. So just as a quick summary, for local version control, you'll create an empty data set with Datalit create. There are configurations. Text to Git is what we use so far, and they are quite useful simply because they do a configuration of which parts of your data go to Git and which to Git Nx. And I'll talk about this in a couple of slides. Then you have this history, that's just the Git revision history to track files and modifications, and Git log or Tika tools that are very beautiful, very useful in displaying things, but you can also use other GUIs because it's just Git revision history. They will be able to display things as well. And there's a Datalit save that will record any modification to the data set. And if you attach a commit message to it, then do it with a -m and summarize it quite nicely. And then I haven't talked about this, but I think I will show it to you later. So keep Datalit download URL in mind. It's a useful command we'll get across in a short while. And then there's Datalit status that reports the current state of the data set. And then you should strive for having a clean data set with no untracked files and no modifications, just to not let anything clutter your data set. Now, the next thing that I think Datalit is really cool for, and if you only use Datalit for one thing, then it should be that, is consuming data. So let me show you a different command, and you've seen it in a couple of screen captures already. And that's the Datalit clone command that here right now gets a GitHub URL to a Git repository hosted on GitHub. So not only can I create datasets to have version control directories on my system, I can also clone them to get a version control directory dataset. The cool thing is that this dataset looks and feels just like a completely normal directory. So you can see here stuff that comes from the Study Forest project, which is a neuroimaging study that acquired naturalistic imaging data during naturalistic stimulation. It's bit structured, and we have all of these subject directories, and it looks like it has a lot of data. But if I issue this command right here, DUSH, that's short for disk usage in human readable sizes, then you can see that it's really quite small, much smaller than you would expect if there would only be a single Nifty file in there. What I can do now is I can run a datalit get command, in this case with a little blob that will expand to all of the files that match this pattern here. And what this command does is actually retrieve the file contents of all of the files that I am interested in. So in summary, or just to say it in other words, when you clone a dataset, it's incredibly lean. You saw how fast the cloning was, and that's because we don't bloat the repository, with those large files, the Git repository stays super lean, and the only thing that is available in the dataset, I can also show it to you in a different subject here, are pointers that allow me to see the metadata, the file names, for example, and then an internal record on where those files are available from, but not their file content, and that makes everything quite lean. So the file content is in a different place than GitHub, where I'm cloning from. And only when I need those files, I can then go and retrieve them, for example, with a datalit get command. What this is really useful for is to have more access to data than my computer has disk space for. And I'm not running into that problem on the compute cluster, but certainly on my own computer, because I can have the complete human connectome dataset, and it only takes up a couple of gigabytes on my computer, and I have access without having to store those files. Now, what I can also do is, once I have retrieved the data and then used it, for example, for data analysis, I can drop it. And dropping means not to lose access to the file, but to simply get rid of the file content, because I don't use it, don't need it temporarily anymore, so that I have freed up the disk space again. And datalit drop is a pretty safe command. It will always ensure that there's a different location where data can be retrieved from, so it will refuse to do it on data that isn't available from other places, and you will have to force it if you really want this. So it tries to be a little bit considerate and prevent data loss. What happens when you drop files is just their file name stays behind, their location information, their metadata, but everything then can be reobtained. So if I now do datalit get again, then it will just retrieve the file again for me. And what this allows, and we're using this frequently in large-scale computations, is very disk space aware workflows. We can install the data, get the data we need, compute the results, and then drop all of the input data and only keep the results, or also only keep results that we can not automatically recompute. So everything is really, really lean, and that becomes very urgent when we start to use data sets that exceed several hundred terabytes. And depending on which field of neuroscience you're in, you'll start to get to these points. Yeah, and this is, for example, also how I would incorporate it into analysis. Start a script with a command that retrieves the necessary files so that it ensures that they are there. Then I do my analysis. In the end, after everything is done, I can drop the data that was used to make everything neat and small again. Alrighty, so now to the distinction between storing stuff in Git or Git Nx. Dorota has already shown you or told you that it's really useful to keep text-based files in Git. And one reason for this is that Git is just very good at storing these files and managing them. But there are also there are also a few other reasons, and I'm going to briefly introduce them. But just to talk about the mechanism, the technical mechanism behind version control with Git Nx, what Git Nx does is it creates a hash that encodes the content identity of a file, and then it uses this hash in place of the file's content to give to Git in order to version control it. So Git only gets to see a couple of hundred characters as a string that encode the file identity, the content identity, but it will never get to see the file content, so it doesn't load the repository. And Git Nx gives the location information to the Git history, but in a secret branch. And then it can manage everything that it controls in the Nx by itself, and that basically is the transport from and to other places. What the user-facing difference between files given to Git and files given to Git Nx is that unless you are on Windows, not the VSL, but on native Windows, is that Git Nx write protects the annexed files to prevent accidental modifications, because that would mess with the content identity hash that is tracked. So in order to modify files that are tracked by Git Nx, you have to do a second step that is called unlocking to make Git Nx aware of, hey, I want to really modify this file. Don't be so protective of it. Let me do a change to it, and that can be cumbersome if you are doing it with text-based files that you frequently edit. So it's useful to keep those small text files in Git so that you have frequent access to them. You don't need to unlock them. Everything just feels completely natural, and you don't realize that there are version control tools working to version your files. And what's also a practical difference is what you've seen here in the clone example. When I'm cloning a dataset, then everything that is annexed is not available right away. For example, all of the files that are just retrieved. The only stuff that's available right after cloning is everything that is in Git. And those can be, for example, the JSONs with the subject information, etc. So if you have stuff that you want to share directly with people, you can put it into Git. Likewise, if you have stuff that you don't want to share with people, you can put it into Git Nx to keep it private, and then ensure that Git Nx will not let other people retrieve the data that you want to keep private. So that's a case-by-case decision depending on the data that you're working with. And we're using this mechanism, for example, with the private, with the sensitive data of neuroimaging, because there are plenty of files that we cannot share with others. And so we use Git Nx in this case to keep them secret, or to limit the number of people that can access them. Now, users can decide quite freely how files are treated, which version control tool gets to see them. And there are different ways in which you can do this. You can use a run procedure. That's the configuration that we used. And text to Git is one that will ensure that every file that is a text file, so every file that is non-binary, will be put into Git. You can also create rules, and there's a full page of tutorials and explanations how to do that in the handbook. You can say all files that are smaller than a certain size, all files with a certain extension, or files in this directory, this specific file. And you can do it also on a per command basis. Either you do a Datalit save to Git, or you do a Git add and Git commit versus a Git Nx add Git commit in order to address the version control tools directly. Now, the next thing that I want to talk about is dataset nesting. Typically, when you have different Git repositories, it's quite cumbersome to link them to each other. It's possible with a mechanism that I don't think Dorota talked about. It's a really, really large pain in the ass. But one thing that Datalit adds to Git repositories is a way to link them in dependency relationships. And I'm going to show you how that looks like by further working on my bits data set in which I will version control files. And what I'm going to do is I'm going to link a dataset from GitHub into this dataset, and this dataset will have DICOM data that I will reproducibly convert into Nifty later. But what I'm doing now is I'm creating a link between my bits dataset and a second dataset that contains the raw data. And this is the schematic process that is displayed here. What you can see here is a very typical scientific use case that is made possible also now with version control, where you have raw data that is the input to a pre-processing pipeline, and the pre-processed data is the input to an analysis, and then the analysis will be the basis of the paper that you write. And if you have all of these in version controlled modules, then you have a neat little hierarchy of things that quite transparently shows everyone what has been done at which point without blurring the borders between those separate entities. And what this does is it modularizes your research. You have several components that are very transparent, but also easily reusable, because your process data is not only the basis for one analysis, but also the basis for another analysis. And if you keep it self-contained, then your second analysis can also link the very same data set and reuse it easily without having to duplicate, for example, storage demands. What this also does on a cultural level or on a reproducibility level is it makes everything quite transparent, because with each of these data sets you have their standalone history, and you can check with those linkages precisely what has been done to which version of the data at which point. So if your raw data changes and you want to redo the pre-processing, then you can do this simply by updating the respective dataset in your hierarchy of datasets. And that opens up the complete provenance of things that have been done to your pipeline that in the end are reported in your paper. And that's a big step forward with regards to transparency. On a technical level, what this also does is it makes things scale, because what Git struggles with is when you have file amounts that exceed, let's say, 500,000 files. Like that's my rule of thumb. You should never put more than 500,000 files in a Git repository. That's kind of the that it also doesn't really matter on the size, just the sheer number of files. But when you have that amount of files, Git will go to its knees and things will become slow in your repositories. Things will fall apart. But if you have the ability to link datasets, then you can modularize it. So let's say maybe you know the UK Biobank dataset, 100,000 participants with all kinds of data. Much too much data to put into a single repository. But once you, for example, conceptualize it as one repository, one dataset per participant, and then nest them into larger structures that are bound together by a top-level dataset, then you have a very scalable workhorse that can version control basically as many files and as much data as you want. And this is how we do it for the UK Biobank dataset and for other datasets that are equally large. And what Datalit does when you nest a dataset, it records where the dataset came from. In the case that you have a lower level dataset, we also call this sub-dataset. And then it records which version of the sub-dataset is installed. So when you take a look into what is written to the history, you will find a sub-project commit that will tell you the exact version of the data that is linked as a dependency, and then also where it came from so that it can be reobtained. And just because it's so much fun, I'm going to add another dataset to my bits data dataset. And this is a Reproducible dataset. It's called Containers. It's a very, very useful resource because it's a collection of very handy containerized softwares that are now available to me. So before I go into the next analysis step, quick summary on dataset consumption and nesting. You can get a dataset from URLs, from paths, from wherever, also from the Open Science Framework if you want to, with Datalit Clone, either on its own, but you can also give it a path where you want to install it to. You can install datasets as so-called sub-datasets within other datasets to nest them. This is done with this little -d dot option that says which dataset am I going to install this in, the current one, so the Unix equivalent of here. And when you do an installation, then everything is really fast because only small files and metadata about the annexed files are present after an installation, and the actual file content can be obtained on demand by means of a datalet get. And then datasets preserve the history, so when you include a dataset in your other dataset, that one will preserve its history. The super dataset, in this case your bits data, will only record the version of, for example, the containers dataset that I have added to it. So the next topic I want to tackle is reproducible data analysis, because your past self is the worst collaborator, and it's sometimes really, really hard to figure out what has been done in an analysis by your past self in order to obtain any given result. And I want to briefly talk about a couple of organizational principles that I'm seeing. Should we do a break though? My dog really needs to take a walk. We can do a short break if you want to. Maybe not a bad idea. Although maybe just 5-10 minutes, if that's all right with everyone.
Especially for the dog.
Cool. Then I'll also grab myself another drink and I'll be right back. And we can also tackle a couple of the installation problems, and then we'll reconvene at 35. Get back to this later. So yeah, a brief detour on good organizational principles for datasets for reproducible analysis. We have a couple of recommendations that are rooted in scientific applications. And one thing is the modularity that I already talked about, to keep everything reusable with sub-datasets and a modular structure, so that you can have this like neat hierarchy that also translates to a neat hierarchy in your file tree. And then what we regard as important is to never modify raw data and not conflate raw data with results, but save those results or computations outside of the input dataset, because after 2 years, you might not remember which one has been the input and which one has been the output if they exist in the same dataset. And it's also much less reusable if you have specific results next to their inputs. And then the last thing here is to keep a super dataset so-called safe contained. This refers to the practice of whenever you have code or scripts that you do not use absolute paths in them, but you make them resolve regardless on which system you're on, so that you can clone your dataset on a different computer and you are not dependent on having the file system exist that you initially ran your analysis on, but it's just a relative path that points downwards to the installed datasets that is required for your script to run successful. And then, in order to keep everything reproducible, there are two provenance things, so information on digital, information where things were created and how they were created. And one is that you record where you got things from, for example, by recording the origin of those sub-data sets, and then also documenting everything in the sense of having some sort of record to know which script produced which output from which data and in which software environment. And the good thing is this later part that is taken care of by a command that's called Datalit run. And Datalit run is basically just a wrapper for whatever command you would run. So if you are to run a script, then you can wrap this script invocation inside of a Datalit run. And what Datalit will do, it will do everything, or it will execute the command for you, and it will make a record of what command was run on which data, and then save all of the results that occurred between starting the execution and finishing the execution and associated with that information. It will save the files and attach a little record to it that has a note on what has been done. And because you already had the session on virtualization, you know that provenance would not be complete without software capture. There is an extension to Datalit that's called Datalit Containers that provides a additional command that does Datalit run, but with software containers, so that it wraps your command execution inside of a software container of your choice. And I'm going to show you how this works. So you already know that I cloned this dataset that's called containers as a sub-dataset. The cool thing is, and you may have already guessed it, containers are simply files. If you have a software container, then it's a kind of a weird file. But unlike, for example, a virtual machine, especially in the case of singularity containers, it is just a single file on your file system. So there's those files are just as easily version controllable as any other file. So Datalit or version control tools for data allow you to version control software alongside it. Because I have included this dataset into my bits dataset, I have access to all of the commands, all of the containers that were packaged with this dataset. So I can now run a command that's called Datalit Containers list, and it lists all of the containers that were created by Dave and other people and shared publicly. And I have access to quite a number of cool things. For example, I have myprep, free server, loads of bits apps, and everything is right there at my disposal. What I can also show you here is that my bits data super dataset has two modular units that are linked. One is code containers, one is input raw data. So I now have a dataset that contains a link to the software that I'm using and a link to the raw data that I'm operating on, so that I'm fulfilling these principles. And what I'm going to do now is a reproducible execution based on those inputs that will save outputs. In my case, bits converted DICOM, bits converted nifty images from DICOM data into the top level dataset. And I'm going to talk a little bit about what happens while this command runs. It takes half a minute on the cluster. What I'm invoking here is a Datalit Containers run command. I'm giving it a commit message because I want to have a human readable description. I'm giving it the container name of the container that I want to use, as well as a specification of the input data and a specification of what will come out of it. And containers run will ensure that the input data is retrieved. So it will issue a get command to get those data first. And it will check if there already is output data from this very same thing that I've specified. And if it finds it, it will make sure that this output data will not interfere with the command execution and unlock it. So what you can currently see is that the command is retrieving all of the things that it needs in order to be performed. The first one was the container, and then it checked whether the raw data is there, and it was already there. And what it now runs is a tool that is called UDconf, and maybe Per will shed some light on it later. What UDconf is it is a powerful DICOM converter that is capable of transforming DICOMs, so the things that come out of an MRI scanner, into NIfTY, that is the data that people that work with fMRI use to do their data analysis. So what the data that I'm using what makes it special is that they were annotated with a specific metadata convention. It's called Repro-In. Notice the name. It's also coming from this group of people. And this kind of metadata convention makes it very trivial to perform automatic bits conversions. The DICOM images already have a set of comprehensive information that is required by bits, such that a converter such as UDconf can automatically infer everything it needs to perform a conversion to NIfTY and the bits conversion. And what you can see here, now I'm going to show you the difference between the current state of the dataset and the one from before running the command, is that I have added bits converted subject to this dataset with a functional fMRI scan, which is really quite neat. So also UDconf is a great tool to use in case that you're working with DICOM images. Now, what this command has done, because I wrapped it in a Datalit Containers run command, is it created a provenance record inside of your Git revision history. And this looks a little bit weird. It's this structured record here that is a machine readable provenance information that not only allows you to kind of guesstimate what has been done, so you can see, okay, this is the code that has been run, and okay, we have some extra inputs, and oh, these are the inputs, these are the outputs, and so forth. The important piece of information is that it can be redone by a machine that can read this information. And I'm going to show you how, but first I'm going to show you how you would publish this data in order to make it available for others. Sorry, first I'm going to do a summary. So you can have Datalit run, and that will record a command and its impact on a data set, and then save all of the modification and associate with them. For this, it's especially important that you have a clean data set, as it will refuse to run initially and tell you, oh, first clean up, I don't want to save anything that's like not relevant to your command. You specify inputs, then they will be retrieved before the command is executed. If you specify outputs, those will be unlocked, so made modifiable, writable in case they are already there and Git Nx wants to override them. And then for containers, for containerized analysis, you can do containers run to capture the software environments as additional provenance, and the command will then automatically be run inside of your containers, and that works with Docker containers or Singularity containers. And then Datalit rerun, which I haven't yet shown you, will automatically re-execute those run records later. So one thing that Datalit tries to do is to make it easy for you to publish your research or share your research or collaborate with your research. So it tries to do this interoperability layer to connect the tools and services that you may already use, so that you can just clone, push, pull to your dataset to all of the locations that you may want to push to. You can, for example, Datalit push something to open a row, or you can do an automatic export to Figshare and give it a DOI, everything with a single command directly from within your dataset. And there are plenty of ways in which you can share and publish data. A lot of them are in the Data Handbook with specific walkthroughs. You can learn how to do it on an S3 bucket, for example, or to Dropbox. But one thing that I want to talk about today, because it's so nice and simple and fast, is Gin. And Gin is a free GitHub, basically. It's a repository hosting service that is based in Germany and created and maintained by the University of Munich. And the cool thing is that it has support for Nx data. So whereas GitHub will tell you, oh God, get away with the Nx, Gin will be able to host your Nx. And it will gladly do so. So you don't have to actually link other places, but you can just push both of your Git repository parts, the Git part and the Nx part, to Gin. And then Gin also has a couple of cool features for open science, because it, for example, can archive a dataset for you and issue a DOI, so that if you do 500 gigabytes of data publication, then Gin will happily take those 500 gigabytes and give you a DOI in addition on top, so that it can be citable. It's really, really quite neat. And I'm going to now do a publication to Gin. And it will be easier with the next release that's coming next month. But here I need to show you the old way of doing it. So first of all, I'm going to log into Gin if I can remember my password. Let's see if that has worked. No. Give me a second here. It's always a little bit scary when people watch. Great. And this is one way of creating a repository on such a repository hosting service. It will look similar on GitHub. And I can create a new repository. And let's say I'm going to call it bits data, because I want to publish my bits data there. Now, importantly, I'm not going to want to initialize this repository with a README, which Gin does as a convenience thing, which is useful in general, but I already have stuff that I want to push there, and I already have a README, so I'm good. And then I can create this README, this repository, and this won't work if you have just registered with Gin. I already had the time to upload my SSH key, and I have a tutorial online how you can do this too. So if you have 10 more minutes, then right now you can upload your SSH key and set everything up, and then things should work for you as well. So what I'm going to do now is I can take this this URL right here, and then add this as a remote, or as we call it in Datalit terms, sibling to my dataset. And the command that I'm going to use here, and I could also use a git command if I wanted to, is siblings add. And I'm going to take this URL and register it under a specific name, in this case Gin, to my dataset as a separate location where this dataset can live. So now I'm going to run this. Sorry, something wants to access my SSH key. And then I have a sibling. And what I can do now is list all of the siblings. In Git's term, this would be a remote, so all of the other places where repositories or datasets are available or that are known, and you can see that one is here and one is Gin. You can also see a warning that's issued by Git Nx because it doesn't yet know Gin very well. It just knows its URL, but it doesn't know of its capabilities. So it says something like, I don't know if I can put my data there. Can you please let me, can you try to let me put my data there to get me some information? And that's what I'm going to do. And in order to publish the data, I'm going to run a datalit command that's called push. And I'm specifying the sibling that I want to push my data to. And that's Gin. And what happens now is that both the Git repository and the Nx of this dataset are published to Gin, so that if I refresh this site here, I have a bad internet connection at home, but also a published dataset that includes all of the data from my subject to etc. And if I were now to be particularly attentive to open science principles and data preservation, I can go to how to publish and find out how I can receive a DOI for this and archive it. The thing that I would need to do is add a datasite file, which is a specific metadata format that Gin requires that includes, for example, authors and stuff. Worthwhile to check out. Alrighty, so now I'm going to show you a last step, and that is rerunning things. And for this, I'm going to create another dataset, because I have now created a pre-processed dataset, or raw, yeah, it's basically a pre-processed dataset. It's raw nifties, but it's pre-processed, right? And now I want to actually do an analysis on this brain imaging data. So I'm creating, outside of this other dataset, a new dataset, because I want to keep everything modular. In this case here, you can see me use a different procedure. That one is called Yoda. It will create a code directory to structure a dataset in a way that makes it particularly suitable for data analysis. It will create a couple of readmes that you can then use to fill placeholders. But you can also read up on the exact things in the chapter, in the handbook on this. And in order to now use my freshly published data, I can either clone it from a local path, but I might be an external collaborator that just gets the link to this Gin repository. So I'm going to clone it from the published Gin repository, and I'm going to add this data as my input data as a subdata set into this new my analysis data set. And now I'm going to run a command that I foreshadowed before. That's a pretty practical command. It's called datalit download URL, that I give a URL to a script that can be found on GitHub. What this does is it not only downloads the script from GitHub, it will also save it, and it will record where it got the script from, so that anyone has the provenance of where this has come from, and it can be reobtained. And now I'm going to add my own container, because it's not only that I want to use published containers, I also have my own containers that I created to share software with. I'm just going to show you how this looks like. For this, I'm going to use a Datalit Containers add command. And in this case, you can see me using an shub URL. So I'm using a singularity container. On the handbook's code along thing, you can also see the respective command for the Docker container if you want to use Docker. And Dorota was so kind to create a Docker container with the required software for this workshop. So what this command does is it instructs Datalit to add a software container to this dataset that can be found in this specific URL. And then it also adds a call format configuration that configures how this command or how this container is executed. And what you can see here is that I'm using a singularity command. The Docker command is in the handbook that says when this container is called in the dataset, then please run singularity exec with the container image, that's a placeholder right there, and the command that is given to the container's run command. And when I enter this command, then what will happen is, first of all, the container is downloaded from its remote source, and then it is registered in the dataset as available software, together with information on how it should be invoked. And what I can do now is, just after I've added the container, use it with a Datalit run. And the script that I've created here is just a random fMRI thing where we extract a little part of the brain to create a mask. So I'm attaching a commit message that I'm computing a brain mask from my converted bits conform data now, and I'm doing this with a Python script. So my invocation is starting with this Python command that calls the getBrainMask.py script. And now, because the input data lives on Gin, it wasn't directly retrieved when I added it as a subdata set. So the command made sure to first retrieve the data. And now it has computed the brain mask. And I can see again in the revision history, for example, also by querying the specific file that was computed here. So I can just say, hey, you file here, how did you come to be? And then that file tells me this person on this date at this time created me by running this command. And what I can do now is I can take the commit hash, the identifier of this thing, and give it to a command that's called Datalit rerun. Or I can, because it's only a single, or because it's like directly available in the history, I can also just run Datalit rerun like this, and it's auto-detected. And what happens then is that the command is re-executed automatically. And if I now take a look at the git log, you can see that there are two commits. And that's special. Normally, when you would re-execute a command and it would result in exactly the same files, binary identical, exactly the same brain mask, then you would only see a single commit. Because when nothing changes in the dataset state, there's nothing to save and nothing to add to the revision history. But because a lot of things with the software that we're using and the data that we're using are subject to slight variations, the talks yesterday already talked about some of that. You can have minuscule differences between recomputations. You can help that with, for example, setting a seed or rounding to a certain decimal precision. That will help. But if you don't do this, it can easily happen that a recomputation creates very tiny differences. And then you can see it creates a second commit, which will have saved your updated results. And you could, for example, compare the two and see what the exact difference is. Or if I would share this analysis with you and you would rerun it on your system and find vastly different results than I would get on my system, then that's something that we can investigate together as researchers to make our research more reproducible. And now I'm going to show you a last thing that's pretty neat, and I make use of it quite frequently. What I'm going to do is I'm going to go again into my bits data set. You can see that it has all of this data that is, like a couple of megabytes large. But what I can do now is to do, I'm just going to drop, let's say, because let's see what happens if I drop everything. Because I have published this data set to Gin, I should be able to drop file content that is available from elsewhere so that I can now save disk space and still have the opportunity to re-obtain it. So let's see, subject 2, give me the nifty that's not available, and I'm going to get it. And I can do the same thing in my analysis data set. I can drop my input data that points to the Gin repository that I've just published and get rid of all of the disk space that I'm currently not using because I've already computed my analysis and only the results, the brain masks, are what I need. And I can get rid of the data that uses up disk space without losing access or the provenance link to this data. So that's a really powerful mechanism, and it gets more powerful the larger the data that you're analyzing are. So to come to the end, and I hope I haven't exceeded the time I was given, in order to find some reasons why to use Datalit, I came up with the following, and they also apply to version control, of course. So whatever you version control, mistakes are not forever anymore, regardless of the file size that you give your revision control tools to track. There's no need for short-term memory anymore when you have run records that let you interrogate all of your data on how it came to be. You can have this disk usage magic where you have access to more data than your hard drive has space. And you have, and I haven't really shown you this, it's quite hard to simulate as a single person, but you have these collaboration and updating mechanisms. So when Alice shares her data with Bob and then fixes a mistake and pushes this mistake, for example, to Jin, then Bob can say Datalit update or git pull and get the changes that were done on the other end of this data set and vice versa. And that allows collaboration on version controlled data sets on data of arbitrary size. And transparency in the context of reproducibility and open science, because you have the history in your data set. There's no need to track down the students that you hired once, that did your bachelor's thesis or their PhD with you. You have their product on your shared file system, and you can take a look into the project, what has been done when the next student takes that project over. And obviously that also applies to your past self. The paper from 2 years ago where someone just asked you mean questions via email or something, you can just take a look into the revision history and find out what was done. So with that, I hope I haven't lost track of time, and I want to acknowledge plenty of people. Joey Has is writing Git Nx, and there's a large team that contributes to Datalit and to the handbook. I've used a couple of illustrations from the Turing Way and Scorpioria collection, and there are a lot of funders and collaborators that I also want to acknowledge here. And I'm terribly sorry for installation problems. I know that it can be a pain, especially if you are using Linux subsystems that, doesn't really come naturally when you have only the Windows experience. So I hope that I have time to fix a couple of things, to investigate problems. We can hopefully talk at a later point